started. So the problems that we're going to do today are problems that will definitely help you with your homework, but they're also stuff that you need to know for tests and just in general that you need to know. So let's see, I did this on a different computer, so let me open it up. We do need to scan something. Thank you so much. And that's not the one to scan. That was from yesterday.
Yeah, I was thinking about doing a Zoom call and going home, but I'm
trying to wait.
Wait, is there multiple people?
Yeah, it's like 4 or 5 of them. Oh, we can't see it.
Okay, so there is the QR code. So if everybody would scan that, please. Whoops. Anybody still need it?
I'm all good.
Everybody good? All right. So the first thing we're going to look at is this question about a synchronous counter with parallel load and a minimum number of additional gates to do this kind of counting. Okay, so first let's figure out what a counter is, and later on I'm going to talk about different kinds of counters besides just up counters and down counters. But the way counters work, and it probably is a little bit familiar to you, or part of it would be from your lab, the one where you did the multiple decoders, would be how you would combine two counters together. But this one is a 4-bit counter. And what you can assume if you are given a problem that says using a 4-bit synchronous counter, you can expect that the counter works. You don't have to make it count. So it's going to do that part correctly. So when it tells you a 4-bit synchronous counter, even if it doesn't give you the picture like we have here, you know that this is what it would look like. And so your counter is going to have outputs, however many bits your counter is. It says this is a 4-bit counter, so it has 4 bits that are your outputs. And it'll have an enable. And because it says it has the ability to load, it also has these 4 inputs, D0, D1, D2, and D3, where it can load. And then it also has a load that tells it to load. And then we're not going to be using this one, the output carry, in this problem. But we could. But we're not using it in this problem. And so when I say it works, what I mean by that is depending on what it starts with. So you'd have Q3, Q2, Q1, Q0. Let's say it starts with 0, 0, 0, 0. Then what you would expect is on the next clock cycle, you would get 0, 0, 0, 1. And on the clock cycle after that, you would get 0, 0, 1, 0. And on the clock cycle after that, you would get 0, 0, 1, 1. And then 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then 1, 0, 0, 0, which 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1100, 1101, 1110, and 1111, and then it'll go back to 0000. And those are the binary numbers for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then back to 0. And if you look at what's going on, and if you look at the circuits that actually make these counters happen, Q0 is going from 0, 1, 0, 1, 0, 1, 0, 1. Q1 toggles every time Q0 gets to 1. So when Q0 gets to 1, Q1 toggles. So we have this 1, and then Q1 toggles and becomes 1. When Q0 gets to 1 again, Q1 toggles. And now if you look at Q2, when Q2 toggles, whenever Q1 and Q0 both become 1. When those are both 1, then Q2 becomes 0. And when they both become 1 again, Q2 becomes 0 again. And when they both become 1 again, Q2 becomes 1. And then what about Q3? Q3 toggles when all three numbers before it become 1. So if you just look at Q0, 0, 1, 0, 1, 0, 1, that'd be Q0. Q2 is going to start at 0, and then as soon as Q0 becomes 1, it becomes 1. And when Q0 becomes 1 again, it becomes 0. I'm sorry, that's Q1. And then Q2 will start at 0 and will stay at 0 until Q1 and Q0 both become 1, and then it'll change to 1. And then Q3, your phone always scares me.
Sorry.
Q3 will be Q0, Q3 will be 0 until all three of them before become 1. And then by doing that, that's how you end up with a counter. Okay, but you don't have to know that. That's what's inside. You don't have to know that. You just have to assume that it works. So your job in this problem is to make a counter that counts from 0, 1, 1, 0 through 1, 0, 1, 1. So 0, 1, 1, 0 through to 1, 0, 1, 1. What decimal number is 0, 1, 1, 0? 6. And what decimal number is 1, 0, 1, 1? 11. So then we'll have 7, 8, 9, and 10. So our counter is supposed to count from 6 to 11 and then go back to 6. Now be careful, because if you look at these numbers on the counter, where is the most significant bit on the counter? At the bottom. So I want to have, I want 1 to go to my enable, because I want my counter to always be enabled. I want my clock to go to the clock, because otherwise it won't advance. And then what I want to load, so I want 0, 1, 1, 0. That's Q0, Q1, Q2, Q3. So I want to load 0 here, 1, 1, 0. But I did a bad job picking a thing to load because it's symmetric, and so you might have put it in backwards. Let's say we started with 7. If we started with 7, then the numbers we would put in would be 1, 1, 1, 0, because our most significant bit is at the bottom. So you read it from bottom to top. 0, 1, 1, 1, 0, 1, 1, 1. But we're starting at 6. Which is 0, 1, 1, 0. And we're supposed to count until we get to 11. And when we get to 11, we want it to go back to 0, 1, 1, 0. So we want to figure out what we can do with these outputs to tell it when to load our starting number again. Well, if I AND together this is Q0, Q1, and Q3. If I AND together Q0, Q1, and Q3, when is that output going to be equal 1? When does this equal 1? When does the output of this AND gate equal 1? Not until I get to 11. Because not until then are all 3 of those bits equal to 0.
That's when it's the load.
And that goes into the load. So the reason that goes into the load is because whenever load is 1, it loads these values. And so we have going into the load something that's only 1 when we get to 1, 0, 1, 1. Now, I could have put in here a not
Yes.
on Q2,
And that would still work.
and that would still work. I just didn't need it, and because I looked at it and I said, well, I'm never going to get 1s on all 3 of these until I get to 11. And I couldn't do anything less than that because I can't see anything. I guess I could have another way I could have done it. I think this would work because I don't think you get 0, 1, 1 anytime until you get to 11.
So you have to find a unique value that isn't repeated from the last.
Yes, and here's a hint for you. If you're not wrapping around, so if I'm not going, say, from 10 to 5, as far as I can tell, getting the 1s will always work. If you are wrapping around, getting all of the bits will always work. There might be a more efficient way, but getting all of the bits will always work. If you're just looking for the most efficient, sometimes there's a more efficient way. Now, I have not known Dr. Trahan to ask about a counter that wraps around, but the other professors do, so I figured I would put one on here. So let's say that we want one, and he might, I just might not have caught him asking it yet. So from 100 through 0011. Okay, so we want to load 1000, So 1, 0, 0, 0. We want 1 to go into the enable. We want the clock to go into the clock. And we want it to reload when we get to Q3 equals 0, Q2 equals 0, Q1 is 1, and Q0 is 1. So I'm just going to write them out and see if I see a clever way to do it. Oh, what was I trying to get to? 0. Okay, there. Oh, 1. No, I'm not there yet. Oh, it's still 0, 0, 1, 1. Oh, there, I am there. Okay, yeah. Okay, so, all right, so I want to go from 1, 0, 0, 0 to 0, 0, 1, 1. Notice a counter on its own wraps around. You don't have to tell it when you get to 1, 1, 1, 1, go to 0, 0, 0, 0. It does that on its own. You don't have to tell it that. So let's look for something unique that will tell it that we've gotten to 0, 0, 1, 1. We know that we can do this. We know that we could take, 1 for Q0, 1 for Q1, 0 for Q2, and 0 for Q3, and all those together. We know we could do that. But is there a more clever way? And I don't know if there is, because I just made this up this morning.
Only like the Q0, Q1, not Q3, or something like that.
Hold on a second, let me make this neater.
Yeah,
So say that again?
it would just be one less. The Q0, Q1, not Q3. All ended for
Q0 and Q1 and not Q2.
3.
Not Q3.
Yeah, that makes sense.
That does work. Yep, that works. Because there's no other time before 0, 0, 1, 1 where we have 1s for Q0 and Q1 and a 0 for Q3. You could also do, I think, no, you couldn't, because we have right there has 1, 1. I was going to say you could also do Q2, but you couldn't do Q2 because Q2 would stop right there. So you could do that, and that would also work. Okay, so any questions on this one?
So you always take your ones from your Q side and you add them together? Or just as a general rule?
As a general rule, what works is if you are not going back to 0, anding together your ones works.
Yes, that's fine.
If you loop back around to 0, you anding your ones and not, anding the knots of your zeros will work. There might be something more efficient than that. So like, for instance, if I wanted to count from 1, let's see, from 0, 1, 0, 1 just to 1,000, or not 1,000, 1000, what would be the only thing I would need to do? So 0, 1, 0, 1, and I'm counting just to 8, to 1, 0, 0, 0. So counting from 5 to 8. Oh, well, that only has one 1. But let's say, I can't think, I'm not coming up with a good example. I'm not coming up with one where I can come up with something easier than getting all of the ones. Maybe there's not one. Yeah, I can't think of one. But yes, so the answer to your question is yes, you and together the ones.
Okay, that's fine.
Okay, other questions? All right.